I hope everyone's doing well. I'm Mr. Ish. Thank you for joining me. Here we're looking at the bromination of hydrocarbons, or you can even call it the halogenation of hydrocarbons. That is, you're adding a halogen group to a hydrocarbon molecule. We will look here at three specific examples, and let the first example be this. We're looking here at cyclopentane. It's a cyclic hydrocarbon, but when you're looking at this, in essence, I'm not showing it, but now I will. You have two hydrogens on each of the carbons, and there's a carbon present at each of the vertices of this pentagon because it represents a chain, a cyclic chain of carbon molecules. You, in essence, have this is what you're really seeing going on. And at the junction of each of these carbons, you have two hydrogens. But what you're seeing here clearly that each carbon atom is similar and exactly the same as everything else. There's no difference here with regards to the substituents that are present on each of the carbons. When you look at any of these carbons, it's a secondary carbon because that specific carbon is attached to two other carbons. This carbon has two other carbons, so it's called a secondary carbon. Because all the carbons over here are secondary, when you do a bromination reaction, there is no doubt as to what you receive as your end product because there is only a single end product. The bromination reaction will be this. You're adding bromine in the presence of some sort of ionization energy or some sort of catalyst which will generate a radical. It will attack because this bromine will split, the bromine diatomic will split into two of these bromine radicals, one of which will attack the cyclic carbon and the other one will attach to a hydrogen. Your end result will be a single type of a molecule and they'll all be the same. It doesn't matter where the bromine attaches, but the name of that molecule will be just the same. This will be your end result and it will be 100% of this because wherever you put bromine it's the same because you could rotate this and make it look like the same molecule plus HBr. These are your end results, but there's no doubt as to this being your end result because all of these carbons are the same. They're all secondary carbons. This right here is the cyclopentane. This right here will be bromocyclopentane as your end result. But again, there's no doubt because each of these carbons are similar to the next. Let's look at this next reaction. We have here a propane. And you know it to be the case because you have 3 points. Here's 1 point, here's 1 point, here's 1 point. Each of those points represents a carbon. If you were to expand it, you're looking at like this. And then you were to make it even more clear, you can generate exactly what is present on each of these carbons. And now you'll see there's a bit of a difference coming here into play. You have here a primary carbon and a secondary carbon. This carbon is attached to only one other carbon. This carbon is attached to only one other. But this right here is attached to two other carbons. It's a secondary carbon. So for clarity's sake, I have a primary carbon here, primary carbon, and a secondary carbon. Your rule that you want to remember is when you do these bromination reactions or halogenation reactions in the presence of this type of a catalyst, ionization energy, the bromine radical will attack and attach to the most substituted carbon atom. And by substituted carbon, I'm talking about the carbon atom that's attached to other carbon atoms. A primary, a secondary, a tertiary, or even an allelic. We're not talking about allelic in here, so we'll cross it out. If you do a bromination reaction, this is most likely to happen in a molecule which has any of these. But if it doesn't have it, then this right here is your next most likely outcome. Then this right here is your default outcome. So keep that in mind. When I'm looking over here at this molecule propane, I have 2 primary carbons and I have 1 secondary carbon. So the bromine will want to attach over here and attack. Your most likely outcome will be this. And we will call it 2-bromopropane because here it's attacking the secondary carbon, and you will also have this other item generate where you will have here a bromine, and this we will call here 1-bromopropane, and this will be the less likely outcome, but it will still be an outcome. This one right here will be the majority of percentage. You can see around 70%. This right here will be less of a percentage, will be 30%. But again, the bromine will always attack in terms of its radical properties the more substituted carbon, and here the most substituted carbon is this internal one. It's secondary versus the primary, so it'll attack here, and that'll be your most frequently seen product in this reaction. Let's look at one more example and then that'll be the end of this video. What we're looking here at this reaction, if you look at this right here, what do I have? I have at the junction of each of these there's a carbon, and let's identify it. I have this and this. This right here is exactly what you're seeing right here with all the atoms identified. What do we have in terms of primary, secondary, or tertiary? Well, this right here is a primary carbon, This right here is a primary carbon because it's attached to only one other carbon. This here is a primary carbon, but this right here is going to be a tertiary carbon because this carbon atom is attached to three other carbon atoms, so it's a tertiary atom. What is the name of this molecule? Well, you have 1, 2, 3, a propane, but you have a methyl group here. You can call this a 2-methyl propane, and that right here is the name of this. You're looking for the longest chain, and then the methyl group is attached to the second carbon atom in that chain, counting from 1, 2, 3, or 1, 2, 3, doesn't matter. It's 2-methyl propane. When you're going to attack this with the bromine group, it can attack any of these, but it's most likely going to attack the tertiary carbon. Your end result here will be this, and you can put your bromine over here. Your least likely product would be the bromine attacking any of those other ones, and then you can say it will be either a bromine over here, or a bromine here, or bromine here, and obviously you'll have a HBr come out. And then what would be the names of these compounds that are developing, and you can picture where the hydrogens are and all of that. Here you have the bromine attached where the hydrogen was. Here the bromine is attached to where one of the hydrogens were on the primary carbon. This molecule right here, you would call that 2-bromo 2-methyl propane, because in the second carbon, counting from either here or from here, the second carbon has a methyl group and it has a bromine group. This right here, this would be your carbon number 1. You wouldn't call this carbon number 1. You want to look for the most substituted item and then count from there. This here would be your carbon number 1. This right here would be 1-bromo 2-methyl propane, and that right here is your end result. This right here would be like 99% of the product. This right here would be only 1% of the product, because that's again the rule you have to remember. In these halogenation or bromination reactions, the bromine is attacking the most substituted carbon. Here's a tertiary carbon, it's going to attack that. It's not going to attack a primary carbon or this primary or this primary. It's going to look for the most substituted carbon atom and attack over there. And your end result here will be 2-bromo 2-methyl propane for the majority. And this will be a very small amount, 1-bromo 2-methyl propane. And that brings us to the end of this video. Thank you.